Hello, good morning, everyone. Can you all confirm if you can hear me clearly? Okay, so I want to welcome you to another uh statistical machine learning class. And of course, today we're going to focus on factor analysis. For those of you that asked about the um a clue on an arrow code on how to load their image, make sure you check the model. I've already attached a clue, okay? So, and I want to appreciate those few that visited my office hour yesterday. So, once again, I want to welcome you to factor analysis. We got a lot to do today, so I need you to pay attention. Factor analysis is very, very crucial. Now, in the outline, I'm going to talk about factor analysis. I'm going to talk about how we estimate factors from data, and of course, how we estimate factor from data. We got principal component method, the principal factor method, the maximum likelihood method. And not only that, I'm also going to walk us through how to choose the numbers of factors. Then lastly, I'm going to talk about factor rotation. Okay, so now let's talk about factor analysis. You know, before now, I walk you through dimensionality reduction technique like principal component analysis, like multidimensional scaling, and and so on, like that. Now, the difference between principal component analysis, in principal component analysis, we actually want to reduce the dimension, in the data set, trying to identify some principal components. And don't forget, those principal components are going to be orthogonal, and each of the components will actually be a linear combination of the old features. And not only that, um, we want to settle for few numbers of principal component that explain the largest variance. Now, in the case of multidimensional scaling, I remember I actually told you that is there a way we can convert data set in high dimensional space to lower dimensional space in such a way that the similarity observed in high dimensional space can also be retained in lower dimensional space. Because I think I walk you through that, and I also walk you through some metric of evaluation, how we can actually know whether the distance is preserved or not. But what is new today is, for instance, if I have some set of variables, okay, and they are correlated. Some of you will ask, how do I know they are correlated? Of course, we can construct the correlation matrix to be able to see whether the variables are correlated. So if they are correlated, okay, in the principal component analysis, we try to construct some principal component, have a reduced version where we construct some principal components, and at the end of the day, the principal components are orthogonal. They're going to be independent, even though initially they were correlating. But there's something that we did not do in principal component. We did not really investigate latent factor that could be responsible or for correlation between features. And that's what we want to do in factor analysis. And that's why it's called factor analysis. The idea behind factor analysis is actually, can we have a way to extract hidden factors The hidden factors that actually cause correlation among variables in the first place. And that is the idea. That's what it's about. Okay. Now the factors are actually called latent. And of course, our aim is to relate that given set of variables that are correlated to a set of common underlying factors that are called hidden factors. Okay. Now this particular model has been for 100 years. It has a long history. Now, I want to go into an example. Okay, if you take a look at this, we got some performance score in different subjects: French, English, history, arithmetic, algebra, and geometry. And we try to generate a correlation matrix because one of the ways to know whether correlation exists is actually to generate correlation between the two pairs. And of course, you're not surprised. The correlation, the correlation here, if you look at the diagonal, okay, if you look at it, we expect French and French to be perfectly correlating. If I have two variables, okay, that are the same, I expect them to be perfectly correlating. And of course, the off diagonal will give you the correlation between any two different subjects. Now, we know correlation exists here, but the question is, can this correlation structure be explained by some factors that we can think about? And that factors, they are not original in the part of this arrangement. Okay, now, let me tell you, I got French, what I'm trying to say now. Performance in French, English, history, arithmetic, algebra, geometry, and we may see that some subjects may actually correlate. For instance, look at arithmetic, algebra, and geometry. Arithmetic, algebra, and geometry, they are topic in math, right? And that was why we said, here the factor could be overall intelligence. It could be science versus humanity, because when you take a look at French, English, history, that is more or less like humanity subject. And when you look at arithmetic, algebra, geometry, we say, okay. So that's exactly what we mean. But you know what? I think I'm going to give you another example apart from this that you can think about. I remember the other time I walk you through US arrest data. In the US arrest data, you have some crime variables like rape, murder, like urban population. Okay. Now, let me tell you this. If you talk about rape, robbery, murder, okay, and crime variables like that, the crime variables like that, they actually correlated. Do you know we could identify some factors that cause them to be correlating? Maybe factors like socioeconomic class, maybe factors like unemployment, because when you look at unemployment, could actually drive crime rates up, and if you take a look at rape, okay, you'll see that what could actually lead to that, maybe if socioeconomic class may actually, lead to we have a more load on rape, because the socio-economic status, can actually, when somebody is experiencing socio-economic distress, I'm actually going to call that socio-economic distress. The socio-economic distress could cause social instability and domestic violence. Okay, and let me also tell you this. Unemployment, can actually load on urban population. Like what I'm trying to say, a city that is highly populated with high unemployment rate, there's possibility of high crime. Okay, so we got so many. Before moving forward, I'm going to also talk about the climate example. When you look at some climate of variables like humidity, like temperature, rainfall, carbon dioxide level, and so on like that. And if those variables are correlating, the underlying hidden factors may actually be seasonal variability, or you talk about global warming. Okay? I think I'll give a lot of example on that. I actually want to move. Now, I want to go into the model now. Let me tell you this. In statistics, whenever we actually want to make an investigation, we need to specify our model. Now, I'm presenting to you a factor analysis model. If I have x1 up to xp, it means I have p numbers of features. They are correlating, and we actually want to explain, want to identify, want to extract some factors, that could cause them to be correlating. So what we're going to do, we actually assume each component will satisfy this. Each component is going to be decomposed into two things. The first one is going to be commonality. The second one is going to be uniqueness. And when you talk about in the commonality, okay, F is going to be the common factors. We assume them to be random, and of course, U is going to be the error. The error is actually a specific variance. The common factor is a shared variance. I'm going to say that again. The common factors, that is actually going to talk about shared variance. Okay, talking about the total variance. We want to talk about the total variance explained by the factors. Okay, then there are some variance that cannot be explained. It is not all the variance that can be explained by factors. So the one that cannot be explained is what we call U, which we call the specific errors. And of course, we're also going to have a lambda JK, which is going to be the loadings. That's a factor loadings. Of course, in a matrix form, we're going to have this way in matrix form. Okay, in scalar form is this. In matrix form is this. And of course, when you take a look at that, in matrix notation, you can see X, that XP by 1. XP by 1 means I'm just talking about X1, X2 up to XP. Okay, the features. Okay, where you have that. Okay, now, and I said, the loading, if you take a look at this guy now, okay, this guy and this guy, they are unobserved. But the only thing that is observed here is X. Okay, is the features. So since they are unobserved, then we're actually going to figure them out from the model. Does that make sense? We're going to figure them out from the model. Now we're going to have assumptions. Let me tell you this. What makes statistical model to be great is when assumption hold. Every statistical model has assumption. A model is as good as assumption put into a model. Okay, so just like every other statistical model, we're going to have assumptions moving forward, because we know F, the factor F, is unobserved. It's going to be a random variable. U is a specific error, also unobserved, also going to be a random variable. We're going to assume they are independent. Okay, we're assuming they are independent, and expected value of the factor and the U equal to 0 because they are unobserved. Okay, the covariance of factor have to be identity. Identity means they have to be, orthogonal. We're assuming that factors are orthogonal. Factors are independent. Okay, and not only that, the covariance of U, don't forget, what do I mean by U? Don't forget, the U is the specific variance. Okay, the U is a specific variance. The covariance of that, okay, is actually represented as that notation. Okay, and let me also tell you this. The unobserved variables U and F, okay, because they are unobserved, they are random variable, we're going to assume they follow Gaussian distribution. Okay, we're assuming they follow Gaussian distribution. Okay. And we also note that this guy and F, they are only defined up to an orthonormal rotation. Orthonormal rotation, we're trying to say the orthogonality is preserved. The angle has to be 90 degrees. Okay. Now, say moving on the model, you know, in the model, the hypothesized model actually going to consider a decomposition of the covariance. If you take a look at what I have here, that's a population covariance, right? The population covariance equal to the variance of X. Don't forget, what is my X? The X are the features, X1 up to XP. And we're decomposing the population covariance into the commonality and the uniqueness. The commonality is actually talking about the total variance explained by factors. The uniqueness is the one that is the variance that is not explained by factor. It is not of, factor cannot explain or variance in the features. Okay, and that's why we call that uniqueness. Now, if you actually, and I said in the diagonal terms, okay, the covariance of xi, sj, j is actually that. Now, in a more precise way, I wanted to see what we mean by total variance. A total variance, okay, the total contribution. Okay, don't forget, we want to maximize, variance. Okay, but let me tell you, the total variance like can be broken down, okay, into what I call, if you take a look at what I have, I told you the other time, if you take a look at this guy now, okay, this is like you are adding the variance of each feature together. Variance of x1 plus variance of s2 until you get to variance of sp. That will be the total variance. Now, that very total variance now can be broken down into the trace. That very can also be called a trace of the variance covariance. I'm going to say that again. Total variance, also called a trace. Why do I say trace? Oh, when you look at the variance covariance matrix, the diagonal is the variances. When you add them all, that's the total variance. Does that make sense? And that is why I said, take a look at this guy. JJ is like, I'm having 1, 1, okay? I'm having 2, 2, okay? You can only have 1, 1, 2, 2 in the diagonal. Does that make sense to everyone? Okay. Now, this is what the factor model is talking about right now. We say, okay, you know what? The total variance, okay, that we also call the trace, can be broken down into explained variance. When I say explained variance, the total variance explained by factors, okay, and the unexplained. That guys, the other part is going to be unexplained. Okay, now if you take a look at what I'm showing you right now, we broke down the total variance into the explained and the unexplained. Okay, now if you take a look at, and that, to be more specific, you can see I said that is the total unexplained. Okay, which is this part. Okay, that's a total unexplained. Okay, and if I want to know the total explained, if I want to know the one that explained by all factors, okay, I'm actually talking about this guy here. You see that? Explained by the k factors. Okay, and let me tell you this: if the numbers of features is p, the numbers of factors is k, that very k should be less than p. Does that make sense? Okay. Now, and if I want to know the variance explained by a particular factor, is just this guy, by a particular factor. And let me tell you this, you can see by a particular factor here, we are only summing from J star from 1 to P. A particular factor, we're looking at the influence of a particular factor on all the features. Okay? Now, that is the explanation of the model. If you really want to understand statistics, we use model. You need to be able to understand all the terminologies in the model. Okay. Now, if you take a look at this example here, let's say, for instance, I don't have data set and I want to simulate. Okay. Maybe I simulate, I'm simulating my factor. Okay. Now, if Z is a factor and I simulated that from a normal distribution, and I also simulated my error. This one is to say I have two different errors. You can see the first error I simulated from normal with a mean 0, standard deviation 1. Another error, I simulated that from a normal distribution with a mean 0, standard deviation 2. Okay. Now, if you take a look at what I'm actually doing here, is to say, there's a connection between feature X1 and a Z. That's it. That's going to be a factor. Okay. And there's also a connection between our feature S2 and a factor. But I wanted to see the contribution of the factor to X1 and S2. In the first one, the Z has a positive contribution to X1. In the second one, the factor has a negative contribution. Okay. At times, let me just say this in the example of this of crime. If you take a look at rape, okay, a rape may have a weaker correlation with maybe unemployment, but rape we have a very strong correlation with socioeconomic status. Does that make sense? So, and some may have a positive correlation with a feature. The other one could have a negative correlation with a feature. So now, what I'm trying to say here is that we normally decompose the covariance into commonality and uniqueness. Okay, now this I need you to pay attention now. This is where I need you to pay attention now. Whenever when we have a model, what is the essence in a model? Like if you take a look at if you take a look at this guy here, give me 1 second. Okay, now when you take a look at this guy here, okay, this is a model. Okay, give me 1 second. Let me give it a befitting one. Okay, let me come back here. Okay, now in a matrix form, this is a model, right? When you take a look at that model, in that very model, we're going to consider, we want to estimate parameters. And let me tell you this, to estimate parameters in a model, we want a situation, we need to be able to look into what is the available information, like the number of independent pieces of information that are available to estimate the parameters. We don't want a situation whereby the number of parameters will be more than the information available. I'm going to say that again. We don't want a situation whereby the number of parameters to be estimated will even be more than the numbers of pieces of independent information. And because of that, we need a degree of freedom. The degree of freedom will strike a balance between the number, because this is what happens. In your model, if you have so many factors, okay, there's going to be so many parameters. If you have few numbers of factors, you're going to have few numbers of parameters. We don't want a situation whereby we're going to be over-parameterized. The model will be over-parameterized. When the model is over-parameterized, that will lead to overfitting. And we don't want a situation where we're going to have maybe the number of factors will not be enough. If the numbers of factors is not going to be enough, then it means the model will not be able to detect the signal that we want, the relationship, the connection that we talk about. Therefore, the degree of freedom will strike a balance. And you know what? Let's first look at each component in the model. You know, in a model, we have a variance, covariance, because we said we want to break down, we want to decompose the variance, covariance. If you take a look at this, if you take a look at this guy here, give me 1 second. So what are we doing? What we're actually doing here is we want to break the variance, covariance, that is the total variance, into two components. The one explained by factor, the one that is not explained by factor. Then we need to be able to know what is the number of parameters available. Okay, now let me tell you this. The numbers of parameters will depend on the numbers of features. Take a look at this. Let me give you this example. If we have three features, the variance, covariance will be 3 by 3, right? Three features, it will be 3 by 3. Now, let's just say P equal to 3. I'm just as, for three features. Now, you know what I need you to do? If you want to know the number of parameter, it's going to be 3. If you plug in 3 here, it's going to be 3 into 3 plus 1 over 2, right? 3 into 3 plus 1 over 2. That will be 3 times 4 over 2. That will be 6, right? It's telling you for three features, the numbers of parameters for variance, covariance is going to be 6. How do I know? Take a look at this. How many diagonal? 3. Then we only consider either this, the one here, or the one here. You don't combine them. You know, there's going to be, because in the variance, covariance is symmetric. Does that make sense? You only consider the number in the diagonal and in the either in the lower part or in the upper part. Because the lower part, the covariance of x1 and s2 is the same as the covariance of s2 and s1. That's what I mean. Now, that is the number of parameters there. Now, you will also need the numbers of parameters in those two parameters too, the lambda, the loading, and the uniqueness. And the numbers of parameters is actually pk plus p. Don't forget, p is the numbers of features, k is the numbers of factors. But you know what? In order for us to have a unique rotation, we will need to impose a constraint. Without imposing a constraint, there's possibility that it's not going to be estimable. Now we're imposing this constraint. The constraint is this guy here. K into K minus 1 divided by 2. That is a constraint. So which means if I want to derive the degree of freedom for the model that will strike a balance between the model complexity, that is the numbers of parameters in the model, and the available piece of information available, that you have in the data. Now I needed to take a look at this. This one, which is the number of parameter in the variance, covariance. Okay, this one, which is the number of parameters, in this and this. Then what are you doing here? You are subtracting the constraints. Okay, with that, you're actually going to strike a balance. The degree of freedom strike a balance. Does that make sense? The degree of freedom strike a balance. Now let me tell you this. If the degree of freedom is negative, then that model cannot be fitted. Does that make sense? So it must not be negative. If the degree of freedom is greater or equal to 0, okay, we may not have exact solution. Okay, so which means there is need for approximate way instead of considering exact decomposition. Of course, you all know that whenever we want to depict a reality, okay, we can never have an exact characterization of reality. There's always going to be a gap, and that's why approximation is going to come in. And let me tell you this. I told you the other time, I said the number, we don't want our number of factors to be so huge. That situation is when the numbers of factors is the same as the numbers of features. In that situation, then your uniqueness is going to be 0. Uniqueness equal to 0 means all the factors we explain, the features, those are with the variance in the feature. Now, how do we estimate factors from data? Okay, we want to know what is the possible number of factors that will be reasonable. Okay, now if you have your FA module, the goal, don't forget, the goal is to estimate these two guys. And we're actually going to replace the sample covariance with the population covariance. Okay, and of course, if the sample covariance is close to being diagonal, okay, then the FA will not be useful. I'm going to explain that. Okay, if the sample covariance is close to a diagonal, the FA will not be useful. The FA will not be useful. Then you're trying to say there is there's no factor to extract. There's no connection. There's no aiding factor that actually explain the correlation among variables. Now, we find a final decomposition. After you have estimated that guy, you can now construct, it means we broken down guys into that. And let me tell you this. Why do you see, look at the sign. I needed to see a sign here. That is saying approximately. It's saying that it's not going to be exactly the same. Okay? If it is not going to be exactly the same, then that will create a minimization problem. We look at the distance. Okay? And so that is that. Now we have a principal component method that can be used. Okay? The principal component method, we go by the way, what we did before when we have, agent decomposition. Okay? And of course, don't forget, we're not going to use all the factors because this is not going to be helpful. We are, in the principal component analysis, you expect the number of principal components should be less than the numbers of factors. Otherwise, if they are equal, there's going to be an issue. So we're only going to choose the one that corresponds to the k largest eigenvalues. Then we have a principal factor method. In the principal factor method, you start with, some initial value for this guy. Then you iterate, okay, until convergence. Okay, you do that, and at the end of the day, that guy, you're actually going to update that. So you keep on updating until convergence happen. But you know what? This is the most popular method, the maximum likelihood method. In the maximum likelihood method, we're actually going to assume that F and U are Gaussian, because before I can use a maximum likelihood approach, I need to know the probability density function, okay, of the data. Now, I'm going to get the log likelihood. The log likelihood now, what are the two? There are two major parameters. The one for loading, the loading, the weight of the factor, and the second one, the uniqueness. Now we're trying to say it's proportional to the log of the determinant of the variance of the covariance minus the trace of the inverse of the population covariance multiplied by sample covariance. And let me tell you this, we're actually going to use EM algorithm. Okay, the EM algorithm, the expectation maximization algorithm, here. And at times situation where the principal factor method has agreement with this method, then we're going to say the FA is appropriate. Okay, how do we choose the number of factors? What I want to do now, I want to walk us through the use of maximum likelihood approach in choosing the number of factors that work. Okay, so let's take a look at that. Now, I said, unlike PCA, the choice of K in FA is restricted by degree of freedom. In the PCA analysis, we don't talk about degree of freedom, but here in factor analysis, okay, the choice of factors actually restricted by degree of freedom. Now, we're actually going to go by way of hypothesis testing. Now, I want to explain this, and I need you to pay attention now. I need you to focus the board. Okay, using the maximum likelihood approach, take a look at this guy. You know what this guy is talking about? That very L is what we call the likelihood of the data given the model. What is the likelihood of the data given the model? Like given the parameters. You really want to know how well the model explains the data. And we can actually equate that to, I needed to pay attention to this, to the ratio of two things. One, that very guy is the covariance implied by the factor model. Why this guy in the denominator is the observed sample covariance. We are looking at the ratio of the two, okay? And that is the reason why in the hypothesis that we are testing, please pay attention. In the hypothesis that we are testing, we are trying to say population covariance equal sample covariance. That is the non-hypothesis. The non-hypothesis is going to say factor model work, because the population covariance is the same as sample covariance, while the alternative is saying it is not equal. Does that make sense? Alternative is trying to say this guy is not the same as a sample covariance. Okay, and when you take a look at this, the ratio here, the numerator is the covariance implied by the model, while the denominator is the sample covariance. And these very tests follow a chi-square distribution. Okay, and with the degree of freedom, you know, when you want to use a chi-square distribution, which means when the non-hypothesis is true, okay, that is the distribution. Okay, and the chi-square approximation can be improved, you know, by this, because the chi-square distribution or the chi-square test that we want to conduct is also sensitive to changing sample size, and that's why the approximation. Now we're going to reject H0 if this happens. If -2 log L is greater than chi-square, with the level, you know, that alpha is a level of significance, which is 0.05. Okay, so I wanted to take a look at that, and you can base your decision on p-value. Okay, which you can base your decision on p-value. Okay, then you also note that the degree of freedom must be positive to apply the test. Okay, because if the degree of freedom is negative, I told you the other time, it's going to be inestimable. Okay, and because of that, we're going to restrict. Okay, we are restricting the number of factors. The number of factors should not be more than that. You see that? What is P? The P is numbers of features. We are doing all of that because we want the degree of freedom to be positive. Now the next is factor rotations. Now let me tell you this. We do factor rotation if we want to make the output from factor model to be more interpretable. Okay? And in the factor rotation, we have, of course, we do that in PCA. What do we use in PCA? Sparse. You remember sparse in PCA? But here, okay, we use rotation, and there are two forms of rotation: varimass rotation. Okay, so the varimass rotation, we ensure that the correlation in the features are not there. So you know, the varimass rotation will ensure that the factors are not correlated. Okay, so but for the PROMASS, okay, the PROMASS, what PROMASS is going to do, the PROMASS will still maintain the correlation value, because at times correlation is still going to be there. But what the PROMASS is going to do, the PROMASS is like, it's an advanced stage of a varimass, where it's going to have a power transformation of the loadings that you have using the varimass. So which means loading with very high will be more large. You're actually doing a power transformation, and loading with a very small value will be smaller by the time you apply you know, the PROMASS. Okay, So I just wanted to take note of that. Okay, so, and then we have what we call a random factor score. This is a matrix. You take a look at what I have here. You have, you know, I said this is a model, right? And F and X. F is a random variable. That's a random variable. F follow a normal distribution. That is 0. Okay, you that. So collectively, the vector, you know, this is like a vector now. Okay, follow normal distribution with a mean vector and the variance covariance. Okay, take a look at that. And we're also going to have a posterior probability given as that, and that is the estimator. But you know what? I'm actually going to quickly move because we don't really need that. Now, I want you to see the way the Farimas rotation and the Promas rotation work. Don't forget I said the two of them is to make you know, the factor output to be more interpretable. Okay, where the Farimas rotation really want to maintain the maximal variance, and for you to maintain the maximal variance, the features have to be you know, unrelated. They have they have to be uncorrelated. But in the case of the Promas, okay, the correlation will still be retained. Okay, now take a look at this. We have data set, and from the data set that we know we have 6 stacks: general, picture, block, maze. Those are 6 stacks. Then this is collected across 112 subjects. And I decided, and you know, I got a covariance. This is a covariance. What you are seeing here is a covariance, and I generated correlation. Look at that. This is a correlation. Okay. The first one, covariance. The second one, correlation. And that's why you see the diagonal 111, right? Now I say a few correlation are large enough to try FA. If you want to try FA, you need to look at the correlation. Like you got 0.58, that is large, 0.57, 0.79. Then you can think of, okay, factor model can actually be applied. Okay. Now, how many factors? Now, these are our code now. You know, based on this, I have a correlation matrix that are generated from the data. I have a covariance matrix that are generated from the data. How do I know the numbers of factors? But what I know for now, what I know right now, the number of factors, the highest it can be is when it is equal to the numbers of features. And that is not even fine, because we want the numbers of factor that will be less than that. And you know what we want to do? We want to do something now. Take a look at this. You know, it is not reasonable to start with the 6 factors because I have 6 variables. Even 5 is too, you know, huge. Okay, but let me tell you this. Well, if you start with 6, it will flash you an error. if you start with 5, it's gonna, like right now, what did I start with? What did I call? I said factor equal to 4, right? What do I see? It's gonna give me an error. Say 4 factor is too many for 6 variables. Do you see that? So if, let's say you don't know, you act as if you don't know, and you just put that in, you're actually going to see an error message. Now, what if you try 3? Okay, if you try 3, you actually see now the degree of freedom for the module is 0. Okay, and when the degree of freedom for the module is 0, there's no way the module is going to fit. Now, I now reduce that to 2 now. When I reduce that to 2, oh my God, reducing that to 2, that I have a result right now. You can see the test statistic is set on 4 degree of freedom. The p-value is 0.191. And let me tell you this. You want to compare the p-value with the level of significance of the 0.05. What do you have in the null hypothesis? In the null hypothesis, you're trying to say the population covariance equal to what? Sample covariance, right? When do you reject? You reject when the p-value is less than 0.05. But right now, what happened? The p-value is greater than. You are not going to reject. When you don't reject, you know what happened? It means that factor is appropriate. Is there any question? Okay. What if I go to factor 1? You know, 2 is 2 work. I also want to see if 1 is going to work. Take a look at this. I'm specifying 1 right now. Oh my God, specify one. Look at the p-value. The p-value is very, very small. The p-value is less than 0.05. Don't go there because you're actually going to reject the null hypothesis. Rejecting the null hypothesis means the population covariance is not the same as sample covariance. Does that make sense? Now, take a look at this. I know that based on 6 features, how many factors work? 2, right? Now, I now want to make my model, my factor model now to be more interpretable. I want to go by way of Farimas. I wanted to see the way how Farimas work and, the Promas that I talked about the other time. Take a look at this right now. Now, based on 2, okay, based on 2 right now, okay. Now, before going by way of Farimas, let me first review the detail about the one that work. We said this guy work, right? Now let's see the model. This is going to be the model. This is the result. You have extracted how many factor? Factor 1, factor 2. Then you're going to have loadings across the features, just like the way you have it in the principal component analysis. Does that make sense? And of course, do you see the uniqueness? These are the uniqueness parts. You're actually going to have the uniqueness for each feature. Now, in another way, okay, this is it. This is the result. If you really want to know the loadings, okay, for factor 1, SS loading, for factor 2, it's going to give all of that, okay? And of course, it's actually telling you that the p-value is greater than 0.05, you're not going to reject the null hypothesis. Because of my time, I'm actually want to show you. Okay, so the Promas, the conventional one is the Farimas. Here I did not indicate Farimas. Okay, the conventional one is the Farimas. Then right now, you can see in the Farimas, what do you see? In the Farimas, you still have of the, if you take a look at that, you didn't lose any information, right? In the Farimas, right? Because the correlation, the variables are no longer, they are no longer correlating. But if you take a look at the Promas, you know what Promas is going to do? Promas is going to be a power transformation of the Farimas. You know what I mean by power transformation? It's going to raise it to a big number. What happened? A large value will become larger, a smaller value will become smaller, which is in a way want to shrink that to 0. That is why you have this. You're gonna see something now. You're gonna see some. Oh my God! Oh, look at that! Missing. Look at that! Some values that are big before become bigger because what am I doing now? I'm actually indicate Promas. Look at that! The rotation Promas. That is what Promas does. But with Promas, you cannot eat your cake and have it. You're going to lose some loadings. Okay, when you lose some loadings, the variables are still correlated, but they are interpretable in a way. So which means Promas, we use Promas when we assume that the features are going to be correlated. We use Varimas situation where we expect there's not going to be correlation. So take a look at that. Okay, so factor 1, factor 2. Okay, so take a look at that. So that is what we just figure out now. Okay, what is the summary? Okay, hypothesis test only apply under the normal assumption which may not hold, and the degree of freedom consideration create artificial constraints. Rotation are choosing subjectively. You have to read literature, okay, to know which one you actually are going to use. Okay, so PCA versus FA, you now see the difference between the two. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.
Surprisingly. Oh, sorry, let me just shut this down.